Here we have a system of three equations with three unknowns. To solve it, we're going to start by writing the corresponding augmented matrix. So the first equation will give us our first row, coefficients 2, 1, 7, minus 3, 2, 1, 7, minus 3, and we denote the constants on the the right-hand side of the augmented matrix separated by this vertical line here. Our second equation will give us our second row. There's no x term, so we'll have a 0, minus 1, minus 4, 2. And our last row will be minus 4, 2, 2, minus 2. Now we'll set about row reducing this to put it in row echelon form. Because there's already a 0 in this entry here, that job is already done for us. So we'll set about putting a 0 in this spot here. And we'll accomplish that by replacing R3 with R3 plus 2 R1. And that will give us, first row will be the same, 2, 1, 7, minus 3. Second row will be the same. And our third row will be 0, 4, 16, minus 8, as you can check. Now, we'll move along. Our next step will be to put a 0 in this entry here. How will we accomplish that? Well, we'll take our new R3 and we'll add 4 times our new R2. And that will give us 2, 1, 7, minus 3. That will in fact give us 0, 0, 0, 0. So now this matrix is in row echelon form. And if we were to write down the corresponding system, here's what we'd get. 2x plus y plus 7z equals minus 3, and minus y minus 4z equals 2. But these are precisely the first two equations we had at the start. So what happened to the third equation? Well, it wasn't obvious when we first looked at the system, but that third equation is a linear combination of the previous two. We learned that through this row reduction exercise. What we now know is that if values x, y, z satisfy the first two equations, they're also going to satisfy that third equation. That third equation doesn't in fact give any new information about what x and y and z have to be. So now our goal is to examine this system of two equations with three unknowns and try to describe all the values x, y, z that make both equations true. Now, because I made up this problem, I happen to know that 1, 2, minus 1 is a solution. I also happen to know, you can check that by plugging those numbers in for x, y, z. I also happen to know that 4, 10, minus 3 is a solution. Again, because I made up the problem, I know those work. But it's maybe not obvious. You just have to plug them in and see that they work. The point is that there's more than one possible set of values for x, y, z. And so what we want is a way of describing all the values x, y, z that will work. What's happening here? Why is there more than one possibility? Because we have two equations with three unknowns. One of the unknowns, or one variable, is what we call free. Which one is free? Well, it actually doesn't matter. You can let whatever one you want to be free, and then the other two will be determined by the free variable. So for instance, I could say, let z be free. And then x and y will depend on z. But I could just as well say, well, let y be free, and in that case, x and z will depend on y. I could also just as easily say, let x be free. Oops. Let x be free. And in that case, y and z will depend on x. It really doesn't matter which one you choose, but just for the sake of clarity, I'm just going to pick one. I'm going to pick this first option here. I'm going to let z be free. So what does that mean for y? What does it mean for x? Well, look at our second equation here. I can let z be anything I want, but then y has to be minus 2 minus 4z. Solve that second equation for y. So no matter what z is, y is minus 2 minus 4z. Well, what about x? Well, let's take this, what we know y has to be, and let's plug it in to here. And remember that z here is free. It can be anything it wants. So when you do that, you'll get 2x plus, and you replace y with minus 2 minus 4z. Then you'll have plus 7z is minus 3. When you solve this for x, you get x is equal to minus a half minus 3 halves z. So there you have it. Z can be anything. Y is then determined in terms of z, and so is x. So here's a perfectly valid way. I'm just going to copy these bits of information down. This is a perfectly valid way of describing all the values x, y, z that make the system of equations true. This is a perfectly valid way here of describing it. But there's another way which really sheds some light on what these sets of values x, y, z really are. And so what we can do, instead of saying let z be free, let's write this here. Let's write, well, z can be anything it wants, so I'm just going to introduce a new letter. I'm going to pick t. And now I'm just going to replace every instance of z with a t. What do we gain by doing this? It seems like maybe a funny thing to do. But what we gain is that now this is the same information. These two black boxes here contain the same information. They're just written a little differently. But this second one here, this is a parametric description of a line. Parametric description of a line. And that might not have been obvious when we were looking over here. Over here. So now that we see that it's, we see through these equations that it's a line, let's just think about that. We started with 3 equations. These 3 equations up here, each of them determines a plane. We row reduced, and we actually found, well, there's really just 2 equations that give information. The third one will be automatically satisfied. Now, these 2 equations are satisfied for x, y, and z along a line. In other words, these 2 planes intersect along a line. I'm going to show you a picture, not just of these 2 planes, but in fact all 3 planes. There's a picture of all 3 planes. You notice that all 3 of them pass through the same line. Interesting.